Okay, I think we'll make a start. So firstly, thank you all very much for coming today, and I hope you have learned something about engineering and about Oxford during your time in Oxford, and have an enjoyable day. So my name is Tom Adcock, and like most academics in this university, I have two jobs. So I am a tutor and fellow in St Peter's College. And you can see some photos here of St Peter's. As you can see, it's either always sunny or always snowy. It's a beautiful place. Please go and talk to my colleague there this afternoon if you would like to find out a bit more about St Peter's. But I'm also an associate professor in the department where I do my research and, of course, also do teaching for the department. Now, the talk I'm going to give today is really drawn partially from a set of first-year lectures which I give to undergraduates in the first 2 weeks of the engineering course on the topic of statics. And we're in particular going to look at this arch structure here. Now, what I'm going to try and convey in this talk is not just a little bit of physics about how arches stand up, but what I really want you to try to take away from this is more a principle. And it's really more about how engineers think about problems, and particularly how we as engineering scientists in Oxford go about tackling problems. And also to try and help you understand why it's skills in physics and in mathematics which are very important, and those are the key things that we're looking for when we think about who's going to get a place in Oxford. And I hope I'll demonstrate to you how we go about problems and why those things are important as part of this talk. So, as I mentioned, this talk is part of a set of lectures on statics. So, statics are a class of essentially structural problems. So it may be an arch like this, it may be something more mechanical where you're trying to carry forces from one place to another, but essentially where we want the structure to stay still. And statics are problems where we can actually solve for what's going on without actually having to calculate the deflections in the structure. So this is only generally possible for very simple structures. So if we're designing this building, if we wanted to actually work out how the loads are being carried from one bit to another, we'd actually have to solve for how all the bits were moving relative to each other, so we could actually work out how stiff different bits are, and we could work out how the loads are being carried that way. But for very simple structures, we don't have to do that. These structures are what we call statically determinate, i.e. we can solve for the static loads without having to resort to working out how they're deflected. So for instance, let's take this structure. So this is our usual representation of something which looks a bit like this bar here. So I'm just resting that on two different points here. Now, I can write down two equations about this. I've got an equation of vertical equilibrium, and I've got an equation of moment equilibrium. We'll come back to those in a few minutes' time when we talk about the arch structure. But essentially, I've got two equations, but I've also got two unknowns, because I've got the load that my right hand's carrying and the load that my left hand's carrying. However, if we think about a structure which is only slightly more complicated, where we've got something in the middle. Now, I'm constrained by my number of hands from actually demonstrating that, and one tends to look ridiculous if you try and balance it on your nose as well, so I'm not going to attempt that. But if we suppose our structure was instead supported in three places, then I'd have three unknowns that I'd want to calculate. But I've still only got those two equations. So we can't solve that problem. This is an indeterminate problem, and we need to use some other techniques. But although statics is, the approaches in this lecture are quite restrictive, there are very few problems we can actually tackle. It's very helpful as an introduction, and it's also very helpful in terms of our background understanding of how loads are carried by structures more generally. And so that's why it's sort of the introductory topic. So in this lecture, we're going to focus on arches. Obviously, we have an arch here, and I'll come back to talking a bit more about that presently. But arches are something we find in many in many structures around the world. And indeed, I hope you're going to go around Oxford looking at several colleges this afternoon, and many colleges have arches either over doorways, spanning gaps. It's a very common type of structure. So let's just think for a minute why it's such a why people design things in arches. Well, essentially, it's quite an efficient way of carrying a load, and that's particularly true for certain materials. So here we've got a concrete arch, and typically actually around Oxford you tend to get brick arches because or stone arches, because that's the standard building material of most Oxford colleges. So why is an arch a good way of carrying that load? Well, if I have two bricks, actually my bricks are just outside, I will just go and nip and get two bricks. Sorry for that. So let's suppose these were two bricks held together with mortar. So if I asked you to break these apart, well, what would you try and do? Well, what you wouldn't try and do is try and compress them, because it's going to be very hard to break, and no matter how strong you are, you're probably going to struggle unless it's a dodgy bit of mortar. But you might try and slide these over each other, or you might try and pull them apart. That's definitely going to be an easier way of breaking something which is made of bricks and mortar. Now, that's not going to be true for steel or something like that, where it's where it's equally strong in tension as in compression. But there are many materials like concrete, like bricks and mortar, where things are actually much stronger in compression. And in an arch, what we have is that's the dominant load is actually being carried in compression. So it's a very efficient way of using that material. That's why it's so widespread, particularly for traditional materials. So just a few other examples of arches. So this is one which some of you may have seen this morning if you came up from London. This is Paddington Station. Most of you are probably trying to work out which is the right train to take, but when you go back, do look up, because Brunel designed these absolutely glorious arches in the ceiling, which are obviously carrying the load from that ceiling down and through these support structures here. The Romans were also, the arch was their basic sort of structural element for spanning gaps, because mainly they were dealing with bricks and materials which were essentially good in compression. And in fact, Roman arches, this is actually an example of a Roman arch. A Roman arch is typically very semicircular, and this arch here is actually more or less semicircular. Arches, as you can see, the shape is slightly different between different ones. Now, you may also have seen this arch. If you came up from London but not on the Paddington route, on the Marylebone route, you may have gone past Wembley on your way up. And again, we're still using arches today. Here we've got an arch, and suspended from that arch is, of course, the roof of the grandstand at Wembley Stadium. A very common structural element. So we're now going to think a bit about a particular problem. So as I've said earlier, to try and demonstrate some general ideas about how engineers, not just structural and civil engineers in all disciplines, think about problems. So what we're going to think about, we've got this arch, and you can see we've got these weights on either side. And what I want to think about is what happens if we take away these weights, which are here. So this is obviously to some extent this is a toy example, but this might be the sort of thing an engineer would be challenged with if you've got an arch structure and you need to maybe have access to this side. What would happen if you removed the things which are helping to hold this in? So what we need to do is we need to find some way of modelling this structure to actually work out what's going to happen when we take away those supporting loads. And the way we're going to do that is we're going to think about the forces on this structure. So why are we thinking about the forces? Well, most of you will have seen Newton's second law, F equals ma, and so if this structure is going to remain standing, we need acceleration to be 0. How can acceleration be 0? Well, that means the resultant forces must be 0. So for it to remain a structure, we need all the forces to balance with each other. That's our basic idea. And in fact, we need all the forces everywhere to balance exactly with each other. So every single block here has to be in equilibrium, i.e. the force pushing this way has to be the same as the force pushing it this way, otherwise it would be moving. And so we're going to try and write down some equations about this thing and then solve them to work out whether this thing is going to move. But before we do that, we need to make a few assumptions. And this comes back to something which is very important about the way engineers work, is that we don't want to model problems which are more difficult than necessary. As a good engineer, you want to find the simplest way of solving a problem. And that's for many reasons. Firstly, that's going to be quickest in terms of your time, and your time is something you're probably charging your client a lot of money for. Secondly, the simpler it is, the easier it is to understand. Maybe it's the case that if it's a simple model, you can think about more scenarios using that model. So my research is on fluid mechanics, and sometimes we run simulations which take 1 or 2 months to run on a supercomputer with many cores. Clearly, when we're doing that, we can't think about many different scenarios, whereas if we had a quicker model, we could. So engineers need to make assumptions, they need to simplify, but they don't need to simplify too far. And indeed, a good engineer is one who really understands the simplifying assumptions they're making. They understand when they're pushing those assumptions a bit too far, and they really understand the limitations. But we want to do things as simply as possible. And the first thing we're going to do to simplify this problem is, instead of actually modelling each of these blocks, we're going to simplify this into a mass centred in the middle of this arch. So essentially, it's just a line. So our arch looks like this. And then the next thing we're going to do is actually analyse just half of this arch. And the reason we're going to do this is actually it just turns out to be simpler in this case. And because we need the whole of this to be in equilibrium, we can really work on any bit of the arch we like and check that all the forces are going to balance on that. So let's think about what equilibrium equations we can write down. So if we start with the most straightforward one, vertical equilibrium. So all the forces going upwards on this arch must equal all the forces going downwards on this arch. So what do we have? Well, we've got the weight of the arch acting downwards, so that's mass times gravitational acceleration acting downwards, and that's going to have to be balanced by some force upwards from the base, which is going to look like this. And so we can write down a very simple equation for vertical equilibrium that reaction force must equal mg. So that's our first equation, but we can't go any further with vertical equilibrium. We've got everything out of that. Now, the next equation is a bit more complicated, and most of you will be familiar with this, but some of you might not. So I think the idea of hopefully of in-line vertical equilibrium like we just did was fairly straightforward. If I want this to remain steady and I push that end, I have to apply the same force in the opposite direction. And then it's going to be balanced. But if I apply a force upwards here, and then I apply a force downwards on this bit, well, those are going to be in equilibrium in the vertical direction, but what's going to happen? Well, our structure is going to move. It's going to start rotating. And this is because the moments don't balance. And so we need to write down an equation of moment equilibrium. So this is where we look at the force and we look at how far that force is acting in a perpendicular direction from some arbitrary point. and indeed you can usually choose any point, but we're going to choose the base of this structure. So if we think about what the moments are about the base of this structure, so we have this mass which is acting somewhere in the, at the centre of mass of the structure, and so if we're taking moments around here, this structure is trying to fall inwards, fall downwards like that. We need to apply something to stop it doing that. But the first thing we need to know is where actually this force pulling it down is acting. Now, this is the maths to do this is something most of you will be familiar with in about a year's time, but to actually work out where the centre of mass is involves an integration in polar coordinates. So we're going to leave that for now, but I hope you're going to take on trust that the centre of mass of this half arch is 0.36 r away from this support. Now, and I hope that seems reasonable, that if r is our radius, the centre of mass is going to be rather closer to one end than the other. So I hope that 0.36 value sounds reasonable. So what's going to actually balance this weight of this structure which is pulling the arch down? Well, we're going to need some horizontal thrust from the other half of the arch. So the other half of the arch is actually providing this force, which I've called here H1. So there's a force acting from this bit of the structure on this bit of the structure of magnitude H1 acting here. And the moment around this point of that is going to be, well, the perpendicular distance. So if we track this on and measure down there, well, that's going to be this length here, r. So the moment that's providing is going to be h1 times r. So we can write down another equation for moment equilibrium. So we've now got two equations to describe what's going on in our structure. But we can't close the problem yet. We're going to need one more equation. And for that, we're going to turn, as hopefully some of you are anticipating, to horizontal equilibrium. So, as well as vertically, this structure all the forces must balance in the horizontal direction. So, this load, H1 here, must be balanced by some force at the base. And that force, the way this is set up, is being provided by a frictional force, and to some extent by these supports here, but essentially those are just providing an extra bit of frictional support on the base. But when we take those away, it will just be the friction between the bottom block and the metal plate and the table, which is enabling this to remain static. Now, most of you will be aware that the way we usually model the frictional force is by saying that it is some proportion of the vertical reaction, what we call Coulomb friction. And we usually say that that proportion is some value which we give the Greek letter mu to, where mu is 0 for a completely frictionless problem and 1 for a perfectly frictional problem. So we've got some parameter mu here. So this frictional force is going to be of magnitude mu r, where mu is a material property. And for this to remain stable, we need that horizontal thrust H1 to be less than this than mu r. Otherwise, these things aren't going to balance, and this thing's going to fall over. So we've now got three equations, and what we can do now is we can look at those equations and we can use our math skills to work out a solution to them. Now, hopefully in this case the solution is not going to be very difficult. It's not going to try the maths of any prospective candidate too much. But of course it could be a much harder problem. Here we've got a fairly simple problem, but it could well be a differential equation or some other problem where it's extremely tricky to work through the mathematics. And that's why, and unfortunately in general, the math is going to be a bit harder than what we're seeing here. And that's why when we're trying to work out who to admit to our engineering course here, that we want people who have really good mathematical skills and, even more important, good mathematical ability and intuition. For now, we can simply rearrange these three simultaneous equations to come up with a criterion that for this to remain stable, mu must be greater than 0.36. So what we could do now, if this was a practical problem, and what we sometimes do when I've got a bit more time, is we can do some experiments. That we can take some blocks like this, which actually have similar frictional properties to these blocks here, and we can do some experiments to try and think about what the coefficient of friction is between these blocks and a surface like that. And one thing you might want to think about is actually how you would actually do that experiment, how you could actually work out the coefficient of friction between two objects in a nice, simple, easy way. But for now, well, I'm going to make an optimistic prediction that this is quite a slippery surface, and so I think we're probably not going to quite have enough friction when I take these supports away, although it's going to be close. But I think what we should do is try this and find out. So if I take the support away, we can see that indeed, in this instance I was right, my prediction was right, and we didn't have enough friction. So I hope what you can see what happened there was that the bottom block essentially there was a force on it going this way. There was not enough force to counteract that going the other way, and so there was an acceleration on it, and the whole thing ended up collapsing. So at least we would have been able to predict that failure were we doing that in reality, and we'd be able to do something about that as engineers. So just to conclude the lecture, a little more on this particular arch and what it was used for. Well, actually it was built by one of our graduate students. She was studying Roman arches, in fact, and she was very interested in studying them, not in places like this, but in earthquake regions, because obviously many Roman arches were built in places where there were earthquakes, in Italy and around the Mediterranean, etc. And obviously many have survived, but what she was really interested in her doctorate was how we could try and improve the survivability of Roman arches. Well, obviously you don't want to be too intrusive into them, they're historic structures, but are there things we can do to make them a bit safer? That's obviously an important thing if you've got people around them, and also to preserve them for the future so that actually your arches will survive the next earthquake. Are there some little things we can do to improve that? And she used this rather simple arch as a model to help her understand the physics of the problem. And so what she did, she put the arch on our earthquake table, which is in the Jenkin building, the original engineering building in Oxford, which is a couple of 100 metres that way. And you can see this is our earthquake table. So the table is rocking, and every time it rocks with a slightly higher frequency and bigger amplitude. And at the moment, this arch is remaining stable, but as the magnitude of the motion increases, we find that eventually it's too much for the arch and it falls over. Now, one thing you might have noticed, though, is that the failure mechanism in that case was rather different to the failure mechanism here. That in that case, the failure was really at the top of the arch, where essentially the force between the two blocks stopped being compressive. And if we've got two blocks which are just being held together by being pushed together, as soon as that load becomes tensile, then they're no longer a structure, then there's no friction between them. And so that's what happened when this one fell over. Very different mechanism to the one we looked at now. And we can just look at this in a slightly different way. So one thing I did was I put my GoPro camera underneath the arch. So this is on the table, so you can see that the camera is actually moving relative to the lights in the ceiling. And we're just obviously looking in slow motion now. And so again, you can see how this thing is failing, that that essentially gets to the point where there's no compression between the blocks, and that's when they fall because there's no friction to stop them moving relative to each other. So what I've tried to do in this brief lecture is to give you a bit of an insight into how engineers tackle problems. That if we are given a challenge, what we need to do is we need to develop a model for that. Virtually all the time that model proves to be a mathematical model because that's the most convenient way of describing the world around us. We build that mathematical model, we then use our math skills to work out what's going on and essentially solve those equations to find out what's going to happen, and we can then make decisions about, well, in this case, the stability of the arch, but it might be about any sort of electrical or fluids or other problem that we might be asked to tackle as engineers. So thank you again very much for coming to Oxford today. I hope you have a very nice day in Oxford and enjoy your time here. Thank you very much.